So suppose you are given a vector bundle like this. So vector bundle has three things: total space, projection map, and the base space. So by abuse of notation, we will call this vector bundle as E. And then you are also given a map from A to B. So then we can construct a vector bundle on A. So this vector bundle E prime can be constructed on A. And if you construct such a vector bundle, it is unique up to isomorphism. So this new vector bundle which you have constructed E prime, you denoted by this F star of E. So let us see this in a figure. So you're given this map F, and then you're given this P. So just given these two things, you can construct E prime. So let us construct E prime. So again, you're given two maps, F and P. So this map F, it takes an element here, it maps it to some element B right here. Now this element B gets lifted to say some element V right here, because this P is a surjective map, so this will get lifted to V here. So this A times E, which we will actually denote by E prime, and then we will shrink this. This is just, you take it as A comma V. So obviously now this diagram is commutative. This F prime takes AV to V, and this P prime takes A comma V to A. So the way we have constructed it, this becomes commutative. Now let us focus on the graph of this function F. So graph of the function F is nothing but tuple this A comma FA. So this is our graph. So how it's going to look like? So we have already drawn a lot of graphs in our life. So this is A, this is B, and this is the graph, just like normal graphs with X and Y axis. So this is A comma F of A. Obviously it lies within this subset of A times B. You're given a vector bundle here, which is E. So we are just trying to show that this A times E actually is a vector bundle. So on A times B, you can construct a vector bundle A times E. So how will you construct it? You will just take this E, and this is our E, and then you will make it A times E. So we are going to construct A times E. So I've constructed A times E. So this A times E, you can see, is lying over A times P. So A times P is a rectangle. So let us see this graph. So corresponding to this graph, we can draw a vector bundle inside, and the corresponding to some base points here, we draw some lines here. So what have we done? So we have constructed a vector bundle on the graph of the function. So now you have this series. So from, you can go to graph of F, which is actually a subset of A times B, and from here you can project onto A. So this A times E has become a vector bundle on A. So this is the proof. Yeah, that is it. And this is proposition 1.5 in Hatcher. So you can read the proof in Hatcher, but graphically this is exactly what the proof will also say. So let us do an example now. So say B is just a point, or say A gets mapped to a point in B. So you have this A, you have this map F given to you, but it maps A to a point. And then you're also given a vector bundle E over B. So you have to lift this point up. So you lift this point up, you get P inverse of this point, which is some vector space. And then what is the pullback vector bundle over A. So pullback of vector bundle would be just A times P inverse of a point. Now P inverse of a point you always know is some Rn. So the pullback is A times Rn. So this is trivial vector bundle. So if A gets mapped to a point via map F, then the pullback will lead to a trivial vector bundle on A. So another example I want to do is the Mobius bundle. This is also taken from Hatcher. For that I will have to erase some of these figures here. So now we want to find the pullback of the Mobius band. So first let us draw the vector bundle on the Mobius band. So say this is the 0 section, then you have I times R. So interval times R 0 to 1, and then I will draw the real line on it. This is the positive part. So this is the positive part of all the real lines, and down below I'm going to draw the negative part of the real lines. So you have this entire thing is one real line. Above we have positive part and below you have negative part, and we have seen before that Mobius bundle is nothing but you connect this part to this part. So we want to find the pullback of this bundle, but before that we are given a map. So we are given a, so you have this Mobius bundle is right here. You have S1, and over this you have this Mobius bundle, and you are also given a map S1 here, which is nothing but takes z here and takes it to z to the power of n. So there are two cases when n is even and n is odd. So let us do the even case first. So when n is even, it is going to attach two copies of this Mobius band to each other. So what it's going to do is, you have so let us keep this like this and draw two copies of this. So the first copy is going to be very similar. So first copy is just going to be like this. Let me draw the positive and the negative part. So this is the first copy. If n is 2, then you have to adjoin this first copy with another copy of this Mobius band. So that is how it will go from one S1 to another S1. So we glue this part to this part, but now this we have two copies, so the second part will get glued to this part here. So this is one, this is second part, this second part will get glued here. So let us glue this part to this part right here. So when we glue this part to this part, this is what we will get. So we have glued it right here because we had to glue this yellow part to this green part. So this comes down. But now this part, focus on this point, so because we have reflected it and glued it. So you have reflected it and glued it. So this part goes on the top. So our gluing is from this side to this side. Now this is just the trivial gluing because you are gluing on the same side. So this was gluing on the opposite side. So if n is even, on S1 you get a trivial bundle. Because when you glue top to top, it is just like gluing a cylinder. Because when you glue a cylinder also, you have this sheet of paper, you glue these two sides, you get a cylinder. You go gluing top part to top part, bottom part to bottom part. So top part to top part means that bottom will get glued to bottom. So you just get a cylinder. It is no longer a Mobius. But suppose now you have n equals to 3. So for all n even, you will get a trivial bundle. But if n is 3, then again we are back in the case that now you have this position here. Say that you have number 3 here. Now you have to glue this part to it. This part to it. So let us glue the green part to it. You extend it and you glue the green part. So we had this point, so you glued this part to it, but now this part is right here. Now the gluing has to be done opposite ends. This end has to be glued with this part. Now these are at the opposite ends. The positive has to be glued with this negative part right here. So what is going now, you will again get a Mobius. So for n equals to 3, you are again getting a Mobius. So you get trivial for n equals to 2 and or n equals to even, and non-trivial for n equals to odd. Now we want to give another definition for vector bundles, because this is important for constructing more bundles out of given bundles. So consider a cover of the base space. So this U is nothing but a union of some UIs. So this is U, the cover of the base space B, and you assign a bundle transition function. So this bundle transition function is this G U1 U2. So what this does is basically to this set it assigns a matrix, and this is very important because say these are two sets you have U1 and then you have U2. So you have some Rn over U1, that is our structure. So there is Rn sitting over here and there is Rn sitting over here. Now on the intersection you want to be able to jump from this Rn to this Rn, and going from one Rn to other Rn requires a matrix multiplication, and that is what the transition function does. It gives us a matrix so that you can go from the total space to total space. Now obviously this is subject to following constraints. It has its inverse. If you go from here to here, you should also be able to come back from here to here. That is this condition. And if you have intersection of three sets, you can go from U1 to U2, then go from U2 to U3, and if you have to come from U3 to U1, you should get identity. So it's not that you pass over a couple of intersections and then you don't know where you ended up. So if you are going from U1 to U2, then U2 to U3, and then from U3 to U1, you should get a identity. So this is called a co-cycle constraint. Now you're given this data, then you can define the bundle as this disjoint union modulo a equivalence relation. So the equivalence relation is B1 V1 is equivalent to B2 V2. So first you should be able to identify the base points. So this is always the case. These two are B, and then these V1 and V2 are identified if you have some matrix which will take this vector V1 to V2. So this matrix obviously you get corresponding to the point in the space, because you see this matrix is associated to the base space. So that's why we are acting on the point B, the same B which is equal to B1 and B2. So you have you identify 2 points in the base if they come from the same point B, and if you're able to go from one vector to another vector via a matrix, and obviously that matrix is dependent upon the base point B. So these bundle transition functions are extremely helpful in constructing new bundles out of old. So say you're given two bundles E1 and E2, then you obviously know its fibers, so you can talk about its fibers. So its fibers are something like Rn. So you can talk about their exterior product, the tensor product. So once you carry out fiber by fiber construction, you also need the transition functions. Now since transition functions are matrices, that is very easy. In the cases of exterior product, now you can take as many exterior products as you want to for as many bundles. Similarly for tensor products. So this construction is fiber by fiber. So you do it fiber by fiber, fiber wise, but then you also have to take care of the transition functions. So for these cases, whatever you do on the fiber, you also do on the transition functions. So everything is preserved. This definition carries out itself. So if you take exterior product of some fibers in Rn, or take their tensor product, then the matrices will act accordingly on the exterior product and the corresponding tensor products. So the definition just carries itself. So whatever operation you want to do fiber by fiber, you also do it on the transition function. So at least for these two things it holds.